Good morning, everyone. Our name is Rowdy Liquid Cooling, and this is our liquid cool thermal test system.
I'm Nicholas Radlett.
I'm Daniel Angeles.
I'm Alex Moreno.
Khalil Sadeh, and our client and mentor is Dr. Cyrus Cheng. So as technology advances, power supplies are becoming smaller, more powerful, and more efficient, and the demand for those power supplies is increasing. And our client, TDK Lambda, needs a test system in order to test these power modules and make sure they comply to safety and efficiency standards. The purpose and objective of our project is to design this thermal test system in order for TDK to be ordered to test these different types of power modules. And this thermal test system must be able to fit on a desktop, and we had a budget of $3,000. For the specifications and functional requirements of our project, we must be able to maintain the power module at 100 degrees centigrade, and this needs to last for 30 minutes, and the variation of temperature cannot be more than 3 degrees Celsius. And this is according to UL testing standards. Our thermal test system must be able to remove 200 watts of heat. It must be leak-proof. It must have universal mounting for different power modules that they will be testing. And it also needs an emergency kill switch, which will also activate emergency cooling.
To begin our design of our liquid cooling system, we started to break it down into the necessary components of what the system must do. 1, it must circulate the liquid, and 2, it must cool down the liquid. To circulate the liquid, we need pump and tubing to control the flow rate of the liquid and to connect all the components together. And to cool the liquid, we would need a heat exchanger and a reservoir to control the temperature of the system and increase its thermal mass.
This is our final configuration of our product. This is a liquid cooling system which uses water as the coolant. The water goes through radiator fans, which removes the heat through forced convection. Our system has a unique cold plate design that maximizes the heat transfer area, which accommodates different size power supplies from TDK. It also has an adjustable Z-axis to accommodate different heights. The water pump and the fans are controlled by a PID controller with PWM, and we have an electrical system that features an emergency stop button.
For our initial design, we started with simulations to ensure that we're able to meet our goal of 100 degrees Celsius. By varying the inlet temperature and the inlet velocity, we were able to achieve that 100-degree goal. And here are snapshots of the simulations for when we apply 200 watts of heat to the cold plate.
This is our mechanical assembly. It features a water pump, a reservoir tank, radiator and fans, as well as the electrical enclosure, which features the smart PID controller and the emergency shut-off button. Our cold plate assembly features a large surface area to accommodate different power supply sizes, an adjustable Z-axis to accommodate different heights of the power supply, as well as the quick disconnect tubing. And for our emergency cooling solution, we use an emergency cooling fan to force high CFM air into the cold plate to cool it down just under 2 minutes when the emergency stop button is pressed. And to show you guys the fabrication process of our product, so here are the pictures of the cold plate brackets and the cold plate block being machined by UTSA Makerspace Machine Shop.
This is a flowchart illustrating all the electrical components in our design. It starts with the emergency switch and the normally closed circuit, which transfers power to the 12-volt power supply. And this powers the smart PID, which in turn powers the thermocouple and max adapter, and the water pump and fans. So for our control system in our enclosure box, we have the smart PID M5 Pro, the thermocouple and max 31850 adapter, the power supply, and then we also have the pump and 12-volt fans. So at this point in time, we are 100% done testing our product. All individual components have been tested to manufacturer specs, and the instrument as a whole has been tested to the predetermined specifications. This is our compliance matrix. It was basically our roadmap for all the tests we put our instrument through. We're happy to say that it has passed all of these tests.
To use as a mock-up for TDK's power supply, we used PTC elements to generate 200 watts of heat at the cold plate surface. And here's the thermal image of the cold plate with 200 watts of heat applied to the surface. And in comparison of the actual data versus our simulation. Our PID was able to keep the temperature variance below the necessary levels for over 30 minutes for a wide range of temperatures. As you can see here, the PID was able to maintain that plus or minus 3 degrees for 100 degrees Celsius.
For our emergency shutoff switch, we designed it to cut power to the testing unit, the radiator fans, and the pump when it's pressed, and activate power to the emergency fan.
Here we can see our earned value management calculations. The team is currently on schedule and within budget, and the team has done a really good job at keeping everything on track and being efficient with our time.
So the liquid-cooled thermal test system successfully tested at 200 watts while meeting the testing standards. TDK wanted dissipation at 200 watts at 100 degrees Celsius, and the team wanted to test the lower temperatures below 100 degrees Celsius to see what the system could reach. As far as the lessons we've learned completing this project, we've learned a lot about project management, teamwork, and how important communication is, what goes into building and tuning a device such as this, and high considerations for thermal mass in a cooling loop.